linear mean square error estimation. It immediately shows two things if you see this title, that in any estimation problem there has to be a signal model. Actually what you are trying to say is that you are trying to estimate some quantity which you cannot probably measure, or I mean you are trying to estimate it in terms of other quantities, or you are trying to predict something whose value is not available, or something is very noisy, so you want to estimate the actual correct thing and you always have the noisy measurement. So in general what happens is that you have some signals at hand which are called measurements, and you want to get something else which you cannot measure directly. That is a typical, that is the estimation problem. Now the thing is that first of all there are two things that will characterize it. The first thing that will characterize it is called a model set. That is, in general the set of, you will have to have some rule of computing that quantity, producing the estimate based on the measurements. In fact that is the estimator. So you cannot, in general, I mean there are so many possible rules, I mean all possible linear, non-linear, dynamic functions, etc., that it is not feasible to leave that question open. So people will generally focus their scope, that okay, if I am looking for a solution to the problem, I am looking for this kind of signal model. Let us say in this class we will see that we will be looking for a solution using a particular kind of signal models. So we will try to find out some estimator which is of that structure. Okay. So that's why this term linear has come. And now there are so many possible linear systems. So the question is, which one of them will you pick up as a good estimator? So you need to define a performance criterion by which you can assess whether the estimate is good or not, right? And there could be several possible performance indexes, and mean square error is the performance index that we are going to consider today. So you see that with every estimation problem there will have to be a signal model, and there will have to be a performance criterion. Then these two things are essential quantities which characterize any estimation problem. Okay. So what do we do in this particular estimation problem? So this is the problem. Initially we consider the problem in a kind of a general setting, and then we will show that this problem can be applied in several practical cases. So the problem is to design an estimator that computes an estimate y hat n of yn. So yn is the signal that we want to estimate. We cannot estimate that value, we cannot measure it. So we produce an estimate of yn which is called the y hat n, and we produce this estimate using a linear combination of data. So these are my measurements. So I have k measurements, k signals, where k varies between 1 to m. Each signal I have at different sampling instance, and based on these k signals at a given sampling instant, I want to generate an estimate y hat n of yn. Now what should be that estimate property? It should be generated such that yn minus y hat n magnitude whole square, in fact you do not need to put magnitude, you can put magnitude if this y is a vector, this y could be a vector in general, but let us think of scalars only now. So yn minus y hat n whole square is minimized, that is, if you use any other y hat n other than using that particular rule which is the MMSE estimator, if you used any other linear estimator, then that will definitely give you a more error. You want to construct it in such a way that among the linear estimators it will give you the mean, it will give you the minimum mean square error. Among the non-linear estimators can still do better. So maybe you could construct a neural network which will give you a still better, still lower estimation error. But among the linear ones, no one will it will not be possible to give a better estimate. So we want to construct such an estimate. So when we say linear combination of data, we mean that I want to generate y hat n using a rule such as this Ckn xn. So I want to compute this is what I want to find out. What are these going to be? Such that if I feed it to a data and generate an estimate, this condition will be satisfied. This is the problem. Okay. Now let us first, so this means that for every time instant I am going to choose a different coefficient, right? At every n for estimating y hat 1 I am going to get a set of m coefficients. For estimating y hat 2 I am going to get a set of coefficients, etc. This is the most general problem. Okay. So let us first see what is the elementary problem which I have to solve if I have to get this. That is, if I want to solve it for some particular n. So if I freeze n, choose n is equal to something, then what happens is that these stochastic processes will now become random variables. So now you have to find a problem such that y hat is equal to ck xk. Find out these ck's. So I am just freezing n, so I am eliminating, I am removing it from the equation. So y hat is now a random variable. Xk's are other random variables which are measured, and I want to actually y is a random variable and I want to estimate y hat based on these random variables using these coefficients. Now what should be the coefficient? That is the question. So now what is y minus y hat? It is y minus, see this equation, if I have k equal to 1 to m, I can always write it like a vector matrix, where this c hat, this is my problem, I cannot write here properly, so I will write here. So what this c hat is a vector. Whenever I give an underbar, it is a vector because I cannot show bold or anything here. It is c1 cn, and this x hat is equal to x1 xm. These are the two vectors. Actually, they are transposes. It is their column vectors. So naturally, this can be written as c transpose x. Okay. So now what do I want to minimize? So I have a performance criterion which is a function of my weight, and I want to minimize it. I want to choose such a c such that the value of this performance criterion will be minimum. So what is the performance criterion? It is expectation of y minus y hat. So y hat is c transpose x, I have just defined. So it is y minus c transpose x into y minus x transpose c. This I have written in this fashion. If it is a scalar, it does not matter because y minus c transpose x is a scalar, so I could have written even whole square. But in general it will be a matrix, so I have written it as if, which will satisfy even a matrix case. So a matrix's norm squared means that x transpose x. So if you say norm, that is if you say x1 square plus x2 square plus x3 square plus x4 square, etc., then you can write it in matrix notation as x transpose x. So I am writing the error vector transpose error vector. Actually this should have been y transpose in that case. Anyway, so now if you multiply, what will happen? You will get expectation of y square. Just multiply this and then you distribute the linear operator, the expectation operator. So you have expectation of y square minus c transpose. C is a constant, so it is not a random variable. So therefore the c transpose expectation of xy minus expectation of yx transpose. This is, if you multiply this to this, you get this term. If you multiply this with this, you get this term. Just term by term multiplication. C transpose, you get this term. So this is how your performance criterion depends on C. Now you have to choose a C which will minimize this. That is the problem. Okay. So that is very simple actually. But before we do that, we need to know the properties of this matrix, expectation of x transpose, or the autocorrelation matrix. Okay. Firstly, obviously R is symmetric. What is the expectation of x transpose? If you have a vector, I have to write like this. I hope you can read this. So if you have a vector x is equal to x1 to xn, it is a column vector actually, then what is xx transpose? The general ijth element of this matrix, this will be a matrix, it's a column into a row. So the ijth element will be given by expectation of xi xj. So obviously the jith element will be expectation of xj xi, which is equal to the ijth element. So this matrix is symmetric. If the jith element of a matrix is equal to its ijth element, then it is symmetric. It is also positive definite. Now what is meant by positive definite? For a matrix, positive definite means that if you take any vector A and evaluate this quantity A transpose R A, this will be a scalar. See, a matrix you are taking, say 2 into 2, you are multiplying it by A transpose and multiplying this by A. So you will get a scalar. This into this plus this into this. This is going to be a row multiplied by a column. This will generally give what is known as a quadratic form. So therefore this, if the matrix R is such that for all vectors A, which only if the vector is identically 0, that is 0 0 0 0 elements, then this has to be 0. Otherwise if you choose any other vector A, it should be non-zero. The R is, it should be positive, the R is such, then the matrix R is called positive definite. Now this R is positive definite. Why? Because if you choose any A, then what is A transpose R A? It is A transpose into expected, I am just substituting this. Now you take this expectation out, then you get expectation of A transpose X into X transpose A. Now this is a scalar, this is a scalar. They are actually the same scalars. So suppose A transpose X is B, then you have expectation of B square, which cannot be negative. So therefore for any other, for all A, R is, this is going to be positive. That's why the matrix, the correlation matrix is positive definite symmetric. Okay, this is a property of R, which is fairly obvious to see. Now let us minimize that. There are two approaches. You can, this is an approach where what I have done is, see, I have just, because I know the result, I have written it. You can see that this performance criterion, this one, let's put it here. Yeah, maybe I can put it here. See, this performance criterion can be cast like this, where D is expectation of xy. See, this is D. This, if this is D, this is D transpose. Okay, so you have, now what I have done now, if you just multiply this, what is going to happen? You are going to get terms like, by the way, A plus B whole transpose is equal to A transpose plus B transpose. So and AB transpose equal to B transpose A transpose. I think you know these things. So suppose you multiply this term is going to give, after this transpose is taken out, it will be C transpose R. R is symmetric, so therefore R transpose is R. This R multiplied by this R inverse will give you identity. Rather this R multiplied by this R inverse. Actually, if you just break it up, you will get that this term, basically this term can be cast like this. That is very simple to do if you just break it up. I don't need to explain it too much. This has been done in one step because the result is known. So now once you can break it up, now you see that obviously this part does not depend on C. This part only depends on X and Y. Okay, so they are in no way dependent on the choice of C. So by choosing C you cannot affect this part. By choosing C you can only affect this part. Now if R is a positive definite matrix, obviously R inverse is also positive definite. If X is positive, 1 by X is also positive. So therefore this term can only be greater than or equal to 0. This is now the vector A. So A transpose R inverse A is greater than 0, because this is positive definite, which means that this performance criterion can only be greater than this. It can only increase by this amount. And when is it going to be least? When this vector is identically 0, or when, so this is minimum if RC is equal to D. If that condition is satisfied, then you get the weight which will make this performance criterion minimal, right? So this is how you get C. This is one way. The other way is, which we all know, that is simply differentiate. Only thing is that here you have vectors, so you have to differentiate with respect to vectors, but that's simple. So the other approach is simply take dPc of dC. Now remember that this Pc is a scalar, it is a performance index, so it is a scalar, and this C is a vector. So what do we mean by differentiating a vector, differentiating a scalar with a vector? This is a standard notation. This actually is a symbol which means this, that it means that dPc by dC1, dPc by dCm. It is a vector. First differentiate Pc with respect to C1, then with C2, then with C3, and put them in a vector. This is a notation which means this. Okay. So now we do, if we do dPc dC1, look at this part. If you just differentiate it, what you will get? This term will go away because it does not have depend on C. And in this term, okay, it is easier to see it from here. You see it from here because they are same. So if you differentiate it with respect to C, this term will be 0. This term will give what? It will give minus C. Rather, it will give minus. This is D. This is D. This is D transpose. So if you take minus C transpose D and then you differentiate it with respect to C, what do you get? You will get D, or rather minus D. Why? Because what is C transpose D? C transpose D is equal to C1 D1 plus C2 D2 plus dot dot dot. So if you differentiate it with respect to any Ci, so dPc by dCi, any particular one, you will get Di. So here you will get D1, here you will get D2, and then at dCm you will get Dm. So you will get the vector D itself back. Okay. So here you get minus D. Here also you get minus D, because C transpose D and D transpose C are same thing. So here you get minus D, here you get minus D, and here what do you get? It's like x square. I mean, you can actually term by term do it and see, but because it is x square, if you differentiate, it is like C square, na? C transpose C. So it is like ax square, right? So if you get that, then you will get twice RC. If you take ax square and if you differentiate it with respect to x, you get twice ax. You can do it term by term, just like I did it here. You can again multiply C transpose, actually take C1, C2, Cm, and then take R11, R12, R13 and do it. There is no problem. So if you differentiate, you actually get this. Now just setting this equal to 0 does not ensure that it is a minimum. You have to also see that the second derivative is positive, only then it is a minimum, otherwise it will be a maximum. So if you do d2pc dc square, that is you again differentiate it with ddc, then you will get twice r, and we know that r is positive definite, so it is greater than or equal to 0. This is a matrix, therefore it is a minimum. Okay. So now if we set it to 0, then we get the same equation back, that is RC equal to D. So the optimal weight must satisfy this relationship, that RC equal to D. Okay. Fairly simple problem, discovered long back in 1940s. Now the question is, how do you solve this equation? So RC equal to D, we have to compute C, so we have to solve this equation. Okay, obviously, as long as we do not go to the computer, do not work by hand, I mean, notationally we always write obviously C naught equal to R inverse D. That is very easy to write, but it is much more difficult to compute. Nobody does R inverse D because I mean, computing R inverse is computationally very heavy. So therefore, obvious way is, I mean, a notational way to say that you compute C naught equal to R inverse D. You actually cannot do that. I mean, you actually should not do that. What is the other way? The other way is to solve the equation RC equal to D, just like you solve AX equal to B by doing Gaussian elimination. So you will find X. So like that you can find C. That is a better way than inverting it. You can also, inversion will be about 3 times more expensive than this. I mean, there exist computational complexity results which will show that if you want to invert, you will spend about 3 times the effort than this. And sometimes what you do is these are advanced methods of numerical linear algebra. That is, if R is a positive definite matrix, then it can be shown that R can be factored like this, where L is a lower triangular matrix. You know what is a lower triangular matrix? That is, elements are like this. Here it is 0. This is lower triangular matrix. So R can always, if R is positive definite symmetric, then R can always be factored as L D L transpose, where this L is a lower triangular matrix, D is a diagonal matrix, and U is basically L transpose is an upper triangular matrix. Okay, sometimes it is also called LDU factorization. So it can be factorized like this. What is the advantage? Why do I want to factorize like this? Because solving triangular set of equations is trivial. If you have this sort of an equation into X is equal to B, it is trivial to solve it. Just you will have x1 equal to b1, then you substitute that, you get x2, you substitute those two, you get x3. It's extremely simple if you triangularize the equations. So if you have LDL transpose, then you can solve it in two simple steps. First you assume that L transpose C is equal to K, some vector. So then you solve LD K is equal to D. See, D is diagonal, so therefore LD is also triangular. So first you solve for LD K equal to D, which is a lower triangular system. Then once you get K, then you solve L transpose C equal to K. That's an upper triangular system. So both are extremely easy to solve. So this is a sort of a modern way to solve these equations, okay, which are also numerically stable. Now there is a beautiful principle which is very profound in linear estimation, and we will come back again and again. That is the principle of orthogonality, which says that the error, that is basic idea is that if you are estimating y, okay, suppose y is a vector in some space, and you are estimating y, let us say with other vectors x, okay. So you have these vectors which are your measurements, and you want to estimate this vector. And in this case, you are generating the estimate by linearly combining x's, which means that whatever is your estimate, it is going to be on this plane. If you take a linear combination of two vectors, it is going to be on the same planes, right? So that means all your estimates are actually in this plane. Now suppose this is an estimate. This is an estimate which you have generated using these two vectors on this plane. So what is the error? Error is this vector. Norm of, that is length of this minus this vector. Now the question is, when is this norm going to be minimum? That is what we want to find. When if you drop a perpendicular on this plane, that is where it is going to be minimum. So which means that the error vector is going to be perpendicular to all these vectors necessarily, right? This is a principle which is satisfied in many cases, and which has a very nice geometrical interpretation. Okay, so what it means, so now the principle of orthogonality says that this error E, which is defined as not only E, not just E for the optimal estimate, not for any estimate E. So now I have substituted the optimal estimate C naught. If you put the optimal estimate C naught, still you will get some error. Let that error be E naught. So y minus x transpose C naught is going to be your E naught. This is the error, right? This is your y hat. So it says that the expectation of x E naught, which means that what is the, that is now this expectation of x and E naught, that is if you take a product of x and E naught, they are going to be, and if you take expectation over all possible random variables, is going to be 0. Why? That you can prove because you have the way you have chosen C naught. So expectation of x into E naught is y, E naught I have just substituted, then I have broken up. So you again get the equation d minus r C naught, d minus r C naught. So basically d minus r C naught, the way I have chosen it, d is r C naught, because it is C naught now. So it is 0. So which means that the error is going to be orthogonal to all measurements that you are using, fact number 1, and obviously since this y hat is generated linearly using all the elements of x, so it is also on the same plane, so it is going to be orthogonal to y hat also. This principle will come back and back and back in most mean square estimators. That is, the moment you want to estimate, want to minimize the length of a vector, which is a quadratic norm, you will always get that the error is going to be perpendicular to the measurements which you use. That's the way to make it minimum length. Okay. So this is a very profound thing which we'll get back. Now let's specialize this case. Previously we did not know what is xk, what is we took a fairly general case, that is xk are some measurements of some other quantities, and y is some other, how they are related, we did not bother, right? So now we'll consider several special cases. For example, one standard problem is to define that if you have a single input. Now I am specializing various cases. That is, now you don't have, previously I had taken k measurements, xk's, and each one I was assuming a vector. Often what we do is we choose, suppose we have some desired response, okay, and we have got some inputs. Now what I want to know is that what is that filter through which if I pass this input I will get this output, very close to this output. This is a valid problem, okay. So then you write, so now we are talking about linear filters, okay. So when we are talking about linear filters, obviously, so now my x1, x2, xm are the samples of the same signal. So now I have, see, I'm now specializing the first problem that I have done. This is a case. We can have many other cases which are of great practical importance, which we can solve by exactly the same method. So here now I am defining y hat n as this. So I am now trying to generate the estimate of y hat n using the past estimates of x, rather using the past measurements of x, and I want to compute these. Okay. So because why I have written it like this? Because this filter is linear, and not only linear, it is FIR, means it is finite impulse response. See, normally the impulse response, if it is an arbitrary linear filter, then it should be H0 m, basically it should be 0 to infinity. If it is a causal filter, if it is a non-causal filter, it should be minus infinity to plus infinity. But so here we are talking about causal and FIR filter. So FIR filter means that after some time the impulse response sequence goes to 0. So only there are finitely many H1, H2, H3, H4 up to Hm. After m greater than 0, Hm is 0. So that's why this summation gets truncated. Okay. So that's why it's optimal FIR filter. And naturally, so you see that estimating this filter is the same problem that we have considered previously. It is our old problem. So H n k we can call them Ckn and put 0 to m minus 1, I can put 1 is equal to m. So this is, I have just changed the indices here and there, and I am trying to show that this is the same problem that we have solved previously. Again I am trying to estimate Ck. Only now my xk's are x n minus k plus 1. It is the samples of the same signal. So it is the same problem. So the problem of estimating this filter such that if you give xn input you will get yn output, close to yn output, is the same problem that we have already solved. So we will get this equation again, only we will have to put appropriate vectors in this case. So in this case what is, so again we will get it is the same problem. So again C0n will give you this Rn, I mean R inverse D, the same thing you will get. Now in this case what does R look like? What was R? R was xi xj. Previously what was R? The ijth element of R is the expectation of xi xj. Now what is xi here? See this is xn. So it is, what is xi? It is x n minus I plus 1. You put I is equal to 1, you get xn. You put I is equal to 2, you will get xn minus 1. You put I is equal to m, you get xn minus m plus 1. Okay. So this is xi. So what is x n minus I plus, so what is it is x n minus j plus 1 expectation. This is Rij in this case. I just put xi xj. Now what is this? This is nothing but the, if the R process is stationary, then expectation of xi xj is equal to Rxx I minus j. It does not depend on what is I, what is j, it just depends on I and j difference. Remember, stationary process, wide sense stationary. So the mean is constant and the autocorrelation is depends only on the difference between 2 points, right. So xt plus tau will give you Rx's tau. So if you do that, you will get, here you will get Rxx 0 up to this. So you will get these terms. So it's again symmetric, you can see, and this is what R looks like in this particular problem. It's just a special case. Okay, and this is what D looks like. So again you have to compute, you have to solve for RC0 equal to D equation, right. See, this is a general problem, okay, general linear signal estimation. That is what we are doing is that we have this signal xk's, these are my measurements, and you have this signal yk. So this is x1. Now that was our original problem. Okay, so in this case we don't have that. In this case what we have is we have only one of them and we have several samples. Okay, so suppose in general I can define a problem in which I can, to generate a particular, suppose I want to generate this one, that is y n. Now the question is what data I am going to use. So I can in general use data from some k1 to k2. If I have the whole strings, suppose I have acquired data using some data acquisition card, I have acquired data and I have got the whole strings x stored in my computer. Then there is no problem, all the values are available. This is not an online case that as signal is coming I want to do something. Signal is already there from, let us say, from 0 to infinity. So then for estimating this yn, I can in general use any time span of x and then see what will be best. Maybe if we vary this we will get better result actually right. So in general I can define a problem in which, and it is also of interest sometimes that we want to generate the, that is using these measurements we can also try to generate xn. That is, we are going to use data from xk1 to xk2. We will not use the value of xn, and we want to estimate what is xn. This is also possible. This problem is of importance because of two things. Because of the fact, for example, we will just see special cases. So we can define an estimator where I want to see I am standing at n, suppose I am standing at time instant n, okay, I am here, this is n. So if I am here, even if data is coming streaming in, then I have all data from 0 to n I have. Now in general I can try to generate an estimate of xn minus I using data from n to n minus m. It is possible, that is I use the data from this to this to generate xn minus I, while I, now you see xn minus I is contained here, so I do not use xn minus I use other things. So that is why you are trying to generate a linear estimator using data from xn, put k equal to 0 you will get xn, put k is equal to capital M you will get n minus m, and you are not using xi, and you want to generate an you are not using xn minus I, and you want to generate an estimate of xn minus I. This is a problem. This is a general problem. Now what are the special cases? A simple special case is put I is equal to 0 you will get a prediction problem. That is, you now have data from n minus 1 to n minus m and you want to generate n, right. So you are using past data to obtain future, that is prediction, which is a very important problem used in many cases. So if you specialize the case for I is equal to 0 you will get a predictor. That is why I sort of, if you just solve a general problem you get everything. Similarly there is there is something called a backward linear prediction. If you see DSP books they will say forward linear prediction and backward linear prediction. Actually backward linear prediction is a bit of a, I am not comfortable with the term because prediction in English usually means going forward. But so basically what backward linear prediction means is that you use, now you see you use from xn to xm minus 1. So you have got future data, and after you got some more data you want to estimate a past value. So you are not going forward in time but you are going backward in time. So you have all your future samples you are using to estimate a past value. That is also, sometimes it is called smoothing. This thing is called smoothing. That is, after you had some measurement now, but after you have many other measurements you can make a better guess of that, especially when the signal is noisy. So in this way you can define several special problems, all of which will form in the same way and all of which can be solved by exactly in the same way by solving the normal equation. That is what I am trying to show. Okay. Now we have what we call this is the origin of this. There is a great mathematician called Norbert Wiener who actually formulated this problem and solved it in 1940s, and actually this Wiener, Kolmogorov, these are the fathers of modern statistical signal processing. So in fact Wiener and Kolmogorov both solved it independently around the same time, this problem. Okay, Wiener solved it in continuous domain, Kolmogorov solved it in discrete domain, and as usual it is known more by the name of Wiener than by Kolmogorov because Wiener comes from the Western world. So here we are defining y hat n like this. What is this? This is a non-causal infinite impulse response filter. So it is the most general case. I am not saying that it is going to be causal, so I have taken minus infinity to plus infinity, and since I have taken up to infinity, it means that it is infinite impulse response. So this is the most general case. Okay. So again the same thing, only thing is that only here there is a problem. What is the problem? The problem is that the number of terms are infinite, so all the matrix sizes, everything is going to be infinite. So you cannot really write a matrix equation here, because the matrix has number of rows, number of columns, everything is infinite. That is why you write it in a different way, but it is the same equation. So you see, again if you apply principle of orthogonality, what do you get? You get each element x n minus k is going to be orthogonal to the error. That is, these ck's should be chosen in such a manner that this is your error, this is your model. So yn minus y hat n is your error. So the error is going to be orthogonal to all the data that you have used to generate it. Principle of orthogonality says that the error is going to be orthogonal to all the data that you have used to generate the estimate which gave that error. So the data which you have used to generate the estimate are these. So if you take any one of them, the error is going to be orthogonal. Correct? And this will hold for all data. Now k varies from minus, so you can take k anywhere actually. Actually this need not be 0, 1, 2, it can be minus infinity to plus infinity. Actually initially I put it for a causal filter, then I have changed the notation, that is why I did not change it here. It should be minus infinity to plus infinity. So if you do that, now this equation you can write in a different way, because you do not, simply because you cannot write it in terms of a matrix, because the matrix is of infinite size. So now you have to write it in terms of in a different way. It is the same matrix again. So now I will write, I will again multiply, and I will put these terms on the left hand side, put these terms on the right hand side. Again now it is an infinite summation. So you get, this is your correlation matrix, okay, Rxy between y. This is no. If I define this as the autocorrelation matrix, x n minus k n minus I will be R xx I minus k or k minus I, all the same. And d of minus k is equal to dk again, and that is x n minus k y n. This is what I am defining. This is clear to you? The correlation matrix. So the correlation matrix will depend on the difference between the indices. So what is what is the index here, n minus k? The index here is n minus y. So what is the difference, I minus k? It's as simple as that. So if you put that, then if you put these notations, these are just notations. I am just in place of these cumbersome sums, I am giving the names. Then I can write this. Then now you put it here. So here you will get ck0 into rk minus I or I minus k, all the same, and dk. So this equation is very famous. It is called the Wiener-Hopf equation. So for this general problem, you have to solve ck by solving what is known as the Wiener-Hopf equation for all k. So you have an infinite set of equations from which you have to solve these elements, these infinite sets of elements. Now what is, how do you do that? How do you solve an infinite set of unknowns from an infinite set of equations? So for doing that, what you can do is, actually what people do is, this is why frequency domain is so useful. Actually there are some cases where you can get nice closed form solutions of this problem. It's not that this problem is not solvable just because you have an infinite number of terms. So for doing that what you can do is, you just observe that what is this? This looks like a convolution integral, no? This is Ck into Rk minus I. In the previous case we had Hk xn minus k, and you are summing over I, right? So you see that you have, this is like a convolution integral. So if you take a Z transform of this, convolution will become product. So then you will get, if you take Z transform on the left hand side, you will get Cz, which is your filter transfer function. After all, what is Cz? These are your impulse response coefficient. So Cz is sigma minus infinity. What is Cz? Cz is sigma minus infinity to plus infinity Ck z to the power minus k. So this term will this is a convolution of convolution of the impulse response sequence with the input, so called input, which is the correlation sequence. So if you take Z transform, here you will get the filter transfer function Cz, and here you will get Sxxz, which is the power spectrum of x. Autocorrelation function, if you take Fourier, if you take Z transform, what will you get? You will get the power spectrum, and this here you will get cross power spectrum of Sx and y. So so what is why did we do this? I mean, what is the beauty of this? Now the beauty of this is that if you can estimate this and if you can estimate this by some other means, then by simply dividing you will get the transfer function Cz, which may or may not be a rational in the rational form. Remember that all transfer functions are not rational, in the sense that every transfer function cannot be expressed as a ratio of two polynomials Bz by Az. For example, there are various cases. For example, e to the power z. E to the power z is not expressible as Bz by Az. It is expressible only if you take an infinite number of terms. So e to the power z is an irrational transfer function. It is still a transfer function, right? So here also you can, at least if you just numerically if you compute Sxx and from the signal, and numerically if you compute Sxy, then simply by dividing these two power spectrums you can get Cz. At least you can get the form. Then you can approximate Cz in some way. But what I am trying to say is that it is practically possible to solve for Cz in some cases. It is not that it is not possible if you go to the frequency domain. So I mean, this is how the Wiener-Hoff equation is generally solved. Okay, and this is why frequency domain is so interesting. See, even 1 by 1 minus z, which is a nice transfer function, it also has an infinite number of coefficients. If you see it as 1 plus z inverse, then it has an infinite number of components. But so what? Doesn't mean that it cannot be represented very compactly using a transfer function 1 by 1 minus z. It can be. So for example, this problem we can now apply to this case. See, this is a very common case. That is, if you have some actual signal y, which is corrupted with some noise v, and this is your measurement x. Now from x you want to estimate what was the actual value. This is one of the central problems in instrumentation. There is some actual process variable, you want to sense it. When you sense it, you get noise mixed with it. So from the measurement, can you get the actual process variable? Standard problem, very common. So what will happen? Now we apply our theory to it. If we apply our theory to it, then we will get that our non-causal filter Hz. So now what is Rxx? Rxx is Ryy plus Rvv. Just take Rxx because y and v are assumed uncorrelated, so all xy terms will get, all yv terms will go to 0. So you get only y square and v square terms. So you get Ryy plus Rvv. There is no cross term here, because I have assumed that y and v are uncorrelated. And now what is ryx? Ryx is nothing but ryx. So if you multiply y here, you will get ryy and you get ryv. Ryv is 0 because again they are uncorrelated. So ryx is ryl. So now you apply this. So you what do you have? You have, what is the optimal filter? It is sxy by sxx by solving the Wiener-Hoff equation in the frequency domain. So you get, so the non-causal filter is syy, in this case so it is syy by, because syx is equal to syy, and here you have to put sxx, which is syy plus svv, right. So if you have some knowledge about the noise, so if you know this and this, you can compute this. Or in other words, if you know even this and this, xx and svv, then also you can compute this, because sxx, if you know, how will you know sxx? You will have to actually take the measurements. X is the measurement, so it is available. So you can estimate sxx, and if you know what is the characteristic of noise, maybe by using very, very expensive and accurate instruments, once you have calibrated what is the exact noise. See, you cannot have that instrument every time because it is very expensive. So once you have calibrated and found out what is svv, now in the field you cannot use that instrument because it is so expensive, because it may be delicate, etc., etc. So in the field you use a normal measurement, get the normal measurement from a sensor which is not so accurate, and then you use your filter, right. That is the idea. So so if you know svv and if you know sxx, then you can compute this filter using this formula. Now this is again, this may be an arbitrary form, but then you can approximate the form using some suitable relationship. That is, you will get some, this will be a general function of z. So now you have to suppose you looking at the function, you say that if I have to approximate this function reasonably well, I have to choose a 6th order filter. Then by choosing coefficients, I can match this frequency domain characteristics. That you can do. So you can estimate sxx and then fit some pole 0 model, 8th order, 12th order, and then if you use that filter, then at least theoretically you can try to get xn. Now still it is a non-causal filter, it uses -infinity to +infinity, those problems are there. So we will stop here today. Only we will note that, see, even for solving this problem there are two central hurdles which I have not addressed in this class. That everywhere we are using this rxx, this sxxz, where do I get them from? So there has to be a way, we have to know, if we have to apply these, we have to know that from a given set of signals, how do we compute its autocorrelation function. Because autocorrelation is, in terms of distribution and all, nobody will give me. People can only give me data. From there I have to estimate its statistical properties. So it is very important to understand how do we, from given a data, how do we compute a power spectrum, estimate a power spectrum, and then use it for, say, in such problems, and how do we compute the autocorrelation. That is very important to know, and that will take up in the next class. Thank you very much.